Uh, this talk specifically is going to talk about Sharon's imaging, the data, and the campaign, very similar to Oliver's talk yesterday morning. I'll then give you an overview of the geology, including geologic features and structures in more detail, implications for the interior, which will be sprinkled throughout the entire presentation, and then end with discussion and conclusions, which will grade directly into a 15-minute-ish Q&A. So, the imaging campaign. This was the last orbit as we approached the system. The imaging campaign actually began years out with New Horizons. Granted, it was just an astronomical object at that time. It was a point spread function size in the detector, but we were still imaging it at least as early as 2013. That said, as we approached, when Sharon was just 10 pixels across, we were able to start to see features on the body. The first thing was we got a dark pole when it was really just 10 pixels across in the detector. So we already, more than a month out, knew that Sharon was going to be an interesting object, much more interesting than perhaps we had thought. It was imaged with the rest of the family, the Pluto system, until the July 4th safing. We missed that last family portrait, but that's okay because we got better data as we kept going. Pluto and Charon continued to be imaged together until a couple days out when they were imaged separately. And this is the last rotation that we got upon approach. And you can see that there is a difference in the pixel scale between the closest approach image there and the 1 day out image there. And by 1 day, I mean one Pluto Charon day, which is 6.38, I think, Earth days. So this is that last rotation, and it allowed us to create a mosaic that we were able to get at better than 40 kilometers per pixel across 80% of the body. Now, for someone who studies the inner solar system a lot more than the outer solar system, me, 40 kilometers per pixel might not sound like a lot. That's only 30 pixels across. But keep in mind, for decades, Charon was just a pixel across. Even with the mutual occultations with Hubble and reconstructing its surface variations, it was still just a few pixels across. So this 30 pixels across is huge compared to what we had before New Horizons. So this is really, really good and neat data that we can do a lot with. That said, the last encounter hemisphere mosaic was at 850 meters per pixel, and we had after that narrowing noodles at up to 160 meters per pixel, which is about twice as coarse as we got for Pluto's best imaging. MVIC also full rotational coverage on approach. We got a last MVIC mosaic, which I think this is, which was at 650 meters per pixel. We also got LISA, that's the imaging spectrometer data, at better than 3 kilometers per pixel. And we were, from those data, able to get a lot of derived products as well. So just like with Pluto, we were able to generate digital terrain models. And Paul mentioned yesterday that he's working to regenerate those. These have a vertical accuracy of anywhere from 0.1 to 1.4 kilometers. That means that some of these are noisy in various areas, and that just has to do with the parallax and the pixel scales. These were rendered at 300 meters per pixel, and from LISA we were able to get mineralogy maps, which Sylvia Protopapa will be talking about later in this session. So now that I've gone over that imaging campaign, I do need to go over the imaging in a little bit more detail just because it gives us a giant asterisk on some of the interpretations that I'm going to be presenting in the rest of this talk. Due to the approach geometry and just how orbital dynamics work and everything else, we basically image the encounter hemisphere at an instant in time in our 14 kilometer per second flyby. That means that the subsolar point where we have effectively noon sun is right at about 50 to 60 degrees north latitude. That means the sun is directly overhead, while the terminator, the sun being at the limb, is closer to down here. The reason why it's black for a lot of the longitude range is because we basically made the mosaic out of successive images as we approached Pluto. This means that we have variable lighting geometry, and some recent studies have shown that when you have the sun overhead versus the sun near the limb, you can lose as many as 99 out of 100 craters. Craters are best viewed when you have good shadowing because you can see those topographic features. Craters, bellwether for topographic features, but it goes for pretty much any topographic feature is best seen when the sun is low. In contrast, reflectivity features are best seen when the sun is high. So some interpretations that I have later about this feature exists here and not here, that comes with an asterisk based on this imaging. The other graphs here are the actual pixel scale that we have, as well as the emission angle, which I'm not going to talk about at all other than what I just said. This is that last day. This is the rotation. This was a movie that we put together very, very early on, and it shows you that variable pixel scale. It's supposed to loop, but because I don't know how to use PowerPoint, I'm just going to go back and forward again. Yeah, thank you. And you can see that discontinuity right there. That's where we have the 40 kilometer per pixel to about 600 kilometer per pixel transition. But you can see that even in the non-encounter hemisphere, so all of this stuff, we still see structure and we see a lot of things that we could never have seen without New Horizons. As one more movie, we have a flyover that we did about 2 months after the encounter, highlighting the dark spot at the pole, which will be talked about also later in this session. We have a large canyon system, not Charon wide, but a very large canyon system, as well as what we'll circle to now, the moated mountains, which are very weird. There are about 4 of them that we know of, probably more elsewhere, but we only know of 4. And those are very strong indicators of a very interesting interior. So the geologic overview, my one slide on this overview is that Charon has a lot of interesting geologic features. I've classified them into 3 different things. One is very commonly observed features that I won't read out. Another is some rare features, such as mottled terrain, which might have analogs on Vesta as well as Mercury. We have layered ejecta craters near and dear to my heart, which I'll talk about in a few slides. We have 2 main physiographic provinces, which is really kind of rare, actually, as well as these massive, massive canyon systems. We also have some features that are almost perhaps never before seen elsewhere in the solar system, such as these moated mountains. We have depressed pits that to me look like a muddy slurp, which I'll talk about in a little bit. And we have these weird, dark, bright crater ejecta patterns. In fact, when I mention these slurps or depressions, there's one right here on the edge. That depression is more than 4 kilometers deep. We have no analog to that really on Earth or pretty much elsewhere in the solar system, and it's really weird. And I will talk about it more in about 10 minutes. First off, the 2 main physiographic provinces. We have Ozterra, this is rotated, north is to the left. We have Ozterra, which is the higher standing blocky terrain, and Vulcan Planitia, which is the lower standing smooth terrain. 2 physiographic provinces, very strange. It's analogous to Mars, and I'm going to make some Mars analogs here, so apologies to people who don't like Mars. This is like Mars in the sense that we have a lower standing smooth area and higher standing older blocky terrain. Now, Ozterra we called blocky in the geologic map paper, and it is characterized by, very oddly enough, large blocks. These blocks are hundreds of kilometers across, separated from each other by chasms that are a couple kilometers deep and up to tens of kilometers across. They are also older than Vulcan Planitia, and this is based on the spatial density of 50-kilometer craters or larger. And the fact that we know that from the craters that we can measure means that it is definitely older because, as I mentioned before, when the sun is directly overhead, you miss craters. And so the fact that we have very likely missed many and yet still get an older age means that Oz is pretty much definitely older than Vulcan Planitia. Vulcan Planitia characterized by smooth terrain, which oddly enough is smooth terrain. The reason why I said that twice is because that's what we called it in the geologic map, smooth terrain. It is lower standing than Oz by about 1 kilometer, and it has a depressed northern rim. So this boundary between Oz and Vulcan Planitia has a depression. It's almost as though we had a slope and then some sort of flow came up to embay it and just sort of stopped. And so you get this depression between the 2. This is one of the first indicators that there is something weird going on with Charon, and that something weird is likely driven by something interesting in the interior. It is very difficult to get this kind of huge, wide resurfacing without invoking usually an impact or melting of some sort, usually caused by an impact. The thing with Charon is that there is no evidence that this was impact caused, unlike, for example, Mars. This is another picture of the blocky terrain, and you can see that we've sketched out some of those blocks. The yellow indicates higher standing terrain, the blue indicates lower standing terrain, and so you can see these are huge and separated by huge chasms as well. Impact craters. I have 3 slides, don't worry, on impact craters. One of them is that this surface does not look saturated, especially for those of us, again, who work more in the inner solar system. It does not look like Charon has a lot of impact craters. But the dynamics of the outer solar system are not the dynamics of the inner solar system. And based on stuff that I assume Kelsey's going to be talking about at 2 o'clock, we will learn that you can still have very old surfaces even with very few impacts, or relatively few impacts. The largest crater that we mapped on Charon is Dorothy Gale. It is up at the north next to this red area. This red area is bound by a scarp that is likely not impact caused. That means that Dorothy Gale is actually small as the largest crater relative to a body of this size. And there might be a larger one somewhere else, just based on the largest crater relative to body size elsewhere in the solar system. My second slide on craters has to do with this bright and dark ejecta pattern. Now, as we approached and we got those initial images that were of the far side, well, the only images of the far side during that last day, we got Charon to be about 50 or so pixels across. And some of us tried to jump the gun and do some initial crater counts. And it was mainly me. I think I was the only one willing to hang my hat on that. And I turned out to be very wrong. What I did was I said, oh, look, there is a dark area and it is surrounded by a bright area. That dark area is probably the crater cavity, and the bright area is the ejecta. Unfortunately, when we actually got resolved or well-resolved images and could see the topography involved, the dark area turned out to be this weird dark ejecta surrounded by bright ejecta, where the crater inside of it was less than half the size of that dark splotch. This is not seen elsewhere in the solar system. This is really strange, and it implies some very strong layering, especially because we only see it in Oz. We do not see this in Vulcan Planitia. However, I have to give that asterisk of the incidence angles. We don't know if we, well, no, we do know we don't see it. We don't know if it doesn't exist. But at the moment, we can say that we definitely see it in Oz, and that means that there is strong subsurface layering going on. When a crater forms, you get inverted stratigraphy. That means that the stuff that is farther away, in this case, the bright crater rays, formed from material that is deeper down under the surface. So we have dark material that's probably been altered by some process, potentially discussed later in talks in this session. And then material that's farther down is likely to be fresher ices that get to be bright when they are broken up and exposed on the surface. This again implies something interesting for the interior. My final slide on impact craters is something that Runyon et al. Will be talking about later today, and that has to do with these layered ejecta craters or abrupt terminus ejecta craters. As far as I know, this is the only paper that calls them abrupt terminus ejecta, and that is because we had one reviewer who absolutely refused to let us use the term layered ejecta, which is the common term in the field. So with that in mind, layered ejecta craters, also sometimes called petals or something else in literature, were first observed on Mars back in the 1970s. The formation of these features is somewhat unknown. There are 2 main classes of models. One is an atmospheric entrainment model, where the impact forms, ejecta comes up, gets entrained in the atmosphere, and gets deposited, and it makes features that look like this. Another class of models is a ground-hugging flow, usually based on volatile mobilization of some sort. So, for example, the impact hits, the energy causes some sort of partial melting or full melting of material that gets entrained in solid material, like on Mars, it would be a rocks of some sort. And then it just forms a flow that hugs the ground and then stops whenever the energy runs out or the material freezes or something like that. Given that Charon does not have an atmosphere, in this paper, we tended to prefer the ground hugging flow model. Now, which of the five in the literature that are out there, we didn't really care. The point was that this was very likely a ground hugging flow of some sort, which meant that there is some sort of volatile in the crust of Charon, which we already knew from other reasons, but this was more information and more backup of that. Now, what's interesting about these features on Charon is that we very rarely see them on other bodies except for Mars. We see one or two on the icy moons, each icy moon of Saturn, for example. After this paper was published, I found one or two on Pluto. Charon, we had a few dozen, which means that Charon has the largest number density or spatial density of these kind of ejecta deposits anywhere in the solar system except for Mars, which I think is really cool and has some interesting, again, implications for the interior. And again, see Kirby's talk later in this session for more on those. All right, moving off of craters, we have grobens or grooves or rills. There were over 500 that were mapped. And remember, in this case, the pixel scale that we're dealing with. The best images of Charon were about 160 meters per pixel. That means that to see these, they already had to be a couple pixels across. So these things are at least a half a kilometer wide for the smallest one, and there are over 500 of them. That's much larger than this building, half a kilometer or a third of a mile. That is very large, and that means that if we can ever go back, we will almost certainly see a lot more that are smaller. Now, with that said, these are extensional features, and we see no corresponding compressional features. It's like the opposite of Mercury, where we see a lot of, now I'm blanking on the term, but the positive relief version of these, wrinkle ridges, that we think is due to global compression. In this case, with Charon, we think that all of these point to a global expansion. And that means that, again, something interesting is going on in the interior. In this case, we have a global expansion of about 1%, and that's likely due to a freezing ice shell of some sort. I mentioned the massive chasms and cliffs that we have. There are approximately 200 scarps that I mapped. Those scarps are several kilometers tall, which means that they are taller than the Grand Canyon in an absolute sense. They're also wider than the Grand Canyon. And again, apologies to people who don't like Mars. This is actually more analogous to Valles Marineris than it is to the Grand Canyon, although a completely different formation mechanism, but in terms of scale. The fact that Charon is actually much, much smaller than Mars means that relative to the body itself, these are enormous. Perhaps they are the largest canyons relative to body size of any body that is known in the solar system so far. These are huge and further imply body-wide expansion. And again, see a talk later this session about some of the implications for that. Next feature of interest is modeled terrain. About 20% of the Vulcan planitia that we could image is this weird modeled terrain. We don't know if these are positive relief features or negative relief features. The data aren't quite good enough to be able to tell, although I don't know the results from Paul's latest photoclinometry, but at least at the time, we couldn't quite tell. If they're positive relief features, then that could imply that there was something like just a rock that was standing there and prevented sublimation of material in this characteristic scale. If they're pits, then we kind of have the opposite situation where we have volatile release pits, perhaps, that then engaged in some sort of positive feedback mechanism to continue to not let go of, but to sublimate these volatiles away while the surrounding surface stayed the same. Next, the moated mountains. Again, one of these first features that we saw once we got to the encounter hemisphere and went, well, that's really weird. So these are these features that are characterized by rough peaks that are high standing above the surface, and they're surrounded by an undulating depression that is below the surface. So it's almost like a dampened sine or cosine wave. These could be a deposited load or kapuka. That's unlikely based on some other folks who have run the numbers, and it turns out that you would need a heat flow likely 100 times what we can actually get in order to have a thin enough crust to respond to that load by depressing the amount that it did. That said, we proposed an alternative in, I think it was 2017, or at least it was 2019, Ross's paper, where these might be foundering blocks that froze in place. And we're actually proposing a sequence where we start off with a large crustal block on this image on the left that has broken off of Ozterra. You can tell that this block is already rotating because the southern end, the southern margin, is much lower in elevation than the northern end. And so what we proposed is that these moated mountains are actually an end state where most of this block has sunk into the surface of Charon, and you are seeing a rotated edge that is standing up still above the surface. What you're seeing in terms of this embayment is, yeah, sorry, drop things. What you're seeing is an embayment of the area that is trying to form now an equipotential surface. So you have this thing that's sinking, and you have something that will flow around it. It's going to try to flow to fill that gap. And we think that what happened was it just got frozen in place as Charon continued to freeze during its thermal evolution. And we even potentially have an end state. These are what I call the muddy slurps. Unfortunately, that does imply a actually they were called depressions or depressed material in the geologic map. I've only recently adopted the muddy slurp idea, but that does imply a formation mechanism where it is a potential end state where the block has fully submerged under the surface, and you are left with just that viscous material trying to form that equipotential surface around it. That said, these could be explained as something completely different. Instead of taking material down, it could be pushing material up. Instead of a slurp, it is actually pushing material up, and it is an effusive vent instead. Especially the fact that we have one that is linear, somewhat linear, curvilinear like this, that could very easily be a large cryovolcanic vent on the surface of Charon today. It froze in place like this, but that could be where source material came up and was deposited on the surface. So what does this imply about the interior in a very brief slide or two to not supplant the talk later today? First off, for lithospheric thickness, we have a brittle thickness that is larger than the elastic thickness that's based on these rift valleys, and we don't see any flexure in these valleys. All we see is basically bookshelf faulting, where it's just snapped apart effectively. We have large craters that don't show any bowed up floors, and that means that the lithosphere has to be strong enough to keep those floors flat. If they were weaker, like we see on Europa, then we would expect to see, or we would see, a bowed up floor on these larger craters. We don't see that. That said, with a thick lithosphere, but evidence for significant rifting with a 1% global expansion, that implies an early global mechanism to account for that rifting itself. That said, all of those ridges and rills that I mapped out, those do not show any trending direction. Now, you might think looking at that image that it really does look that they sort of run in general like this. However, I think that's an artifact of the lighting, as well as this massive canyon system itself is sort of telling your eye, hey, look at me and look at everything parallel to me. When you actually map these out and run the statistics, you see no trending direction. And that means that this freezing, assuming that's what formed it, this freezing happened before the two bodies, Charon and Pluto, were tidally locked. Otherwise, you would see a trending direction if this happened during despinning or after that tidal locking. And we also see no tidal bulge on Charon at all. It is round to within the ability of us to measure it if you take into account all of the topography. Without a tidal bulge, this must have happened before that tidal locking. Further evidence of something interesting in the interior, some liquid of some sort. We have these smooth plains that appear to embay the fractured Ozterra. Those smooth plains show a lot of different morphologies that really strongly imply that there are volatiles there. Again, as I think Sylvia will talk about later, we definitely see volatiles in the spectral signature. We have these moated mountains, which really strongly imply a viscous flow. All of this activity is extremely old, but I think that the conclusion is, well, I think, and many other people think, that this is perhaps one of the best, I'm not going to say proof, one of the best evidences of any sort of effusive cryovolcanism anywhere in the solar system, where we have just this massive, smooth plain that really displays a lot of features that look like a volcanic flow of some sort. And given the composition, it would have been a cryovolcanic flow. This is a nice sketch that shows two potential different, very similarly related scenarios. I'm going to leave it up and vamp for about 5 to 10 seconds while you take a picture or a screenshot, because there's a lot of text on here that I don't want to read, but it really does show these crustal blocks that are breaking off, poking through the surface to form those moated mountains, and the material coming in to embay them. Now that you've taken the picture, if you wanted it, I'll move on to the next one. And we have the PowerPoint cartoon that shows something similar. But we have an undifferentiated body on the left that fully differentiated, including having a liquid ocean under an ice shell. That liquid material, whatever it was, such as an ammonia hydrate, perhaps, that is almost, but not quite as buoyant as water ice, could have still been forced up through fissures in the surface uh, in the presence of a freezing ice shell providing that pressure. As well as if you just tweak things a little bit, you can get that density inversion that you need. Meanwhile, as heat continues to go down, you freeze entirely, and that's where we are today with Charon. So this is my last slide. I'm again not going to read the discussion or the conclusion points. If you are interested, take a picture or a screenshot, but I will vamp and read out that last bullet point, because when New Horizons flew by, the North Pole was oriented down effectively in the solar system, and we did not see Charon or Pluto entirely. That said, orbital dynamics can kick you as well as lift you back up, because in 2119, Charon and Pluto will be oriented perpendicular to the sun, or that pole will be perpendicular to the sun, and so we will be able to see the entirety of both bodies if we time it right and send a spacecraft out there. So that is going to be my suggestion to also stick around for Carly Howitt's talk on Thursday afternoon. And again, I want to thank you for listening and thank the organizers for inviting us to give this talk.
Thank you, Stuart. Guess we'd better start putting the proposal together for that. So we have about 15 and a half minutes for questions. And it's, okay, well, take one in here, then I'll go to one online, and then we'll have some more in here.
Jason Hofgartner, Southwest Research Institute. Thanks, Stuart, for a great talk. My question is about the three unique features that you mentioned, the moated mountains and the depressions and the crater eject bright dark patterns. You kind of suggested that they're unique, but then you also said like that they're maybe not quite unique. Can you just elaborate more on that? Like, what are the places where you've seen something somewhat similar to these?
So the bright dark ejecta, I have not seen widespread elsewhere at all in the solar system, and I've looked at a lot of craters, 3 million plus, and actually I can't think of any case that really stands out for those. In terms,
Will
what?
Will has a large dark
Okay.
deposit that extends beyond the rim as well.
See, my knowledge of the Jovian and Saturnian satellites is low. So okay, Pwill is one, but still, I mean, the fact that we see these around a couple dozen on Charon, it's a lot. That said, so you also asked about the moated mountains. So we do see, so Kapuka is the Hawaiian term. We see those in Hawaii, oddly enough, where in that case it is a deposited load where there's just a mountain sitting there and it has depressed the material around it. In terms of those deep mud-like, ropey, undulating is a good word, descriptive term, depressions. Um, Again, I'm not sure if there's an analog in the solar system that's as deep as these are, especially relative to the body. I mean, 4 kilometers for a 600-ish kilometer radius body is what, about 0.5-ish% of the body size. That's huge. And I can't think of any that we see elsewhere.
Okay, I think we'll just go to one online. This is from Mark Elowitz. Can the gravitational interaction between Pluto and Charon affect their respective geology over geologically long timescales, or is the interaction too weak?
I'm going to defer to a later talk because I don't know the answer to that question. Sorry. I am hoping that Chloe talks about it in the Bedingfield and Roden talk on implications for the interior.
So Stuart, easy question. Why is the structure of Charon dipolar? I can only think of another example, and that's our own moon. I don't know if this or other examples of it, but it's this overwhelming thing that sorted itself out into a dipole.
Yeah, you said it's an easy question. I don't know. I have not seen anyone suggesting why it's like that. I mean, it might not be half and half. Again, we got only about 30% at this good resolution.
I thought though it's sort of the far encounter stuff.
We see some evidence
for at least a number of longitudes.
Right. We see that evidence for it carrying off onto the far side, but we don't know, for example, what's south of the Terminator. We don't know how far it really carries over to the far side. It is a very large difference, and as an impacts person, I would suggest that it could have been triggered in the south by potentially an impact. Perhaps you have I was about to say a mantle plume, but I don't think that there's nearly enough heat to cause that sort of melting on Charon that would preferentially melt a part of it. And in my search of the literature, I didn't see anyone suggesting why it would be like that, just a dichotomy, as opposed to just Oz fracturing and sinking in various other places. But Paul might have an idea.
I just wanted to be sure. Are you referring to the resurfacing in Vulcan Planitia and then the Highlands dichotomy? Is that what you're referring to?
It's what you see right here. Nothing but,
diagonal
yeah, I can.
Yeah. Okay. That relates to my question, Stuart. Anyway, because I actually wrote the hypothesis in the 2018 paper at first, so I know something about this. The basic hypothesis is that the northern hemisphere is fractured into these large blocks. And they remain intact, but in the south, they foundered. And so for some reason, it just never went to completion. It started in the south, went to partial completion, and
you still, that's
left
a
the north
description. You
intact.
still have a dipole by some physical mechanism.
Right,
did that,
right.
So.
I don't know why it didn't go to completion. That's the unknown question. Maybe it just cooled too quickly or something. I don't know. But yeah, I do agree very strongly with the idea that these are foundered blocks, and that the moated mountains are just little peaks of blocks that are basically subsided, and that the mud splats are basically the viscous material trying to close up on that. My question relates to the statement at the end that this was cryovolcanism. This mechanism doesn't really sound like the canonical volcanic hypothesis where you get molten material coming up on top of the crust. This sounds like a total replacement process. So how does Ross, and how do you define cryovolcanism in this sense? Are you advocating two different things at the same time? That's what I'm trying to get at.
So in terms of what first caused the dichotomy that would then lead to this area being potentially resurfaced, again, I'm going to defer to you in that hypothesis, or another hypothesis if someone has it. We sort of say after that, what happened with this ice shell is that it had fissures or cracks formed by whatever process, including these foundering blocks and just expansion. And there was some weakness that cracks propagated along. And then it's through those that material came up and formed these effusive flows. So that's sort of how we're defining the effusive cryovolcanism, is that the material came up through these cracks and was deposited. Now, what caused that initial difference, just like with the Luna Maria, what caused that difference in terms of here's a large impact basin, and so material was easier for stuff to come up and form those floodplains. Not entirely sure in this particular case. And again, I must have missed your paper. Apologies in my review.
That's fine. We'll talk about it later. But the basic question, I think, is, yeah, I think there's agreement that these are founded blocks, but the question is, how was it materially replaced? Was it the asthenosphere that came up and sort of swamped over it, or was it something else? And maybe we have to move on. But.
Paul, I know we've talked about this a little bit before, but I'm wondering if you're asking more about the definition of cryovolcanism.
In this particular case.
Yeah. So I've gone with a very general definition just because all the features that we see that could be cryovolcanic are very different across different bodies. But if you have a large volume of material that comes from the subsurface to the surface and basically replaces that new surface, there's maybe a few other things you could call it besides volcanism. You could maybe call it extrusive diaparism if there's no melt involved or something, right? Yeah. But I think generally people do call it volcanism if molten rock comes to the surface, right? Is there a case when that's not true?
Yeah. So whether it was molten at that particular time.
Right, but if it was like had a tiny fraction of melt.
But if this is wholesale lithospheric replacement, is that really what we would call on Earth volcanism? So
I think
semantic difference, but it's
right. That's why I was wondering if it's more just a nomenclature question in a way, because
it's not a process we seek.
Yes. Yeah.
Ariel might be the only other example, but
yeah. Anyways, I think that if you call it cryovolcanism,
in new territory, I think
people are really excited about it. If you call it extrusive diaparism, maybe some of us in the room are really excited about it, but not.
I mean, we were
not the general public.
We were talking yesterday about, what we were expecting from the Pluto encounter, and people were afraid Charon would look like Rhea, but thank God it doesn't. It looks like something totally new. So, I mean, this is not a complaint at all. This is a happy thing. Very happy.
So yes, under what you said, Kelsey, we were taking a very broad definitional terms. Molten or partially molten or liquid or viscous material coming to the surface and recoating it, that is what we were terming as cryovolcanism or effusive cryovolcanism.
Joel Parker with Southwest Research. I was just wondering if this difference between the two halves could be reflective of the season, the pole orientation at the time of some event, or the time scales way too off for that to be a factor?
I think the time scale is way too off for that to be a factor.
Hi. One question that I have, you probably know that the best model to explain Pluto and Charon, like the formation, is a giant impact, right, by Robbins canopy. And in that model, the impactor, the proto-Charon, had about 3 times more mass. So how does that fit with the geology that we see?
So my understanding is that it doesn't matter, in the sense that that impactor is going to be, you're going to lose almost everything from the surface of that impactor. You're going to lose a lot of that original information. And so not much is my response.
Meaning that you think that model does not fit with the observation, or that it does fit with the observation?
Neither. I don't think it really matters in this case. I mean, if Sharon was captured, it would still be okay. Whereas if Sharon were a giant impact or what was the term yesterday? I can't remember. Was it the kiss and go or something? Kiss and capture? Yeah, right. It's still there. If it was a kiss and capture, then it also doesn't really matter in that sense.
Thank you. So carryless APL. Stuart, do you care to speculate on what is the subsurface ice that is in your layered ejecta? I'm going to make an argument. It probably isn't just simple water ice because you would have seen that on plenty of other bodies of the solar system. Is it carbon dioxide? Is it ammoniated water like maybe Dale Cruikshank would like to see?
Right. So I spent about 5 extra hours yesterday reading several other papers to try to prepare for just that kind of question.
Good.
So I don't particularly have a preference because I'm not a spectroscopist and I don't do any of this modeling. But from what I could find, it was mostly an argument that it was ammoniated ice of some sort. So an NH3 H2O combination that can get you close to the density inversion that you would need in order to actually get that material to rise, especially if there were any sort of impurities in the ice shell that was covering it that would change the density a little bit. Or just again, that freezing ice is going to, water ice freezing is going to expand. And so you can get that pressure buildup so that you can get the material to come up through any cracks that are there or force itself up. So yeah, I think that at least from what I could tell, the preference, although I think Sylvia potentially is going to respond to that as well. So I'll stop vamping and.
Okay. Thank you.
Stuart, another question, and this is with timescales and how you lay out the history of what happened. When you mentioned, that Karen is very unsaturated, one thing I thought about right away that I have not heard, at least, I haven't heard the conversation about, is that one little area of Pluto in Cthulhu that is extremely saturated. And I might have presumed, although I don't know this is true, that the creation of Charon, would have obliterated such a thing. Is that possible? That was a fossil before. If not, then you were able to do that on Pluto, and there's no analog, of that anywhere on Charon, at least that we've seen. So I'm wondering how you fit all the time scales together here, what happened when.
So first I'll ask Kelsey, are you planning to address that at all? Okay. So then I would speculate, again, this is speculation, that Pluto was formed first. It was doing its thing, accumulating craters. Charon came across. Charon came, the proto-Charon formed after an impact that either completely reset or very, very mostly reset Pluto. And then Charon was still forming while Pluto was already solidified and resolidified and capturing forming impacts as well. And so there was a period of time where Charon was still not able to record any craters on its surface, while Pluto still could. And so with that said, I'm right at 2 o'clock, but Sylvia, if you wanted to correct me on the ammonia clathrate.
No, I don't want to correct you. What I wanted to say, though, is that we need to keep in mind that the small satellites have a similar composition to Charon in terms of ammonia and water ice. And I don't think we are here to invoke cryovolcanism for those. Just a note.
Okay. Yeah, thank you very much, Stuart.